Okay, last time we covered the heat equation here, and this is a differential equation, and to solve it you need boundary conditions. You need boundary conditions, and if it's transient you'll need initial conditions. So this won't take very long, but let me show you typical boundary conditions. Okay. One would be a constant surface temperature. So we'll just say constant surface temp. Okay, so if you have a border here, an object, let's say this direction is X. If this temperature is constant, we'll call it TS, then the boundary condition would just be at X equals 0, comma, the temperature is just equal to TS. The temperature is constant. Okay. A second boundary condition that you might have is a constant heat flux. Okay, and with this problem here, what you would have is we'll call it Q dot double prime S. Hang on just a minute, I need to go turn off the TV. Okay, so here we would have a constant heat flux, Q dot double prime S. Okay, so at X equals 0, what we'd have is minus K dt dx is equal to Q dot double prime S. So if you solve for delta T, delta X, so if that's true, then delta T delta X is equal to minus Q dot double prime S divided by K. So that would be a scenario where you have constant heat flux. Okay, so at X equals 0, right here, dt dx is equal to all this, and this will all be known. Okay, a third boundary condition that you might have would be adiabatic. Surface. In other words, of course, you know from thermo, adiabatic means that this surface is insulated. Okay, and you know your heat, the temperature profile might do something like this, where if there's no heat transfer going into the surface, what that means is Q dot is equal to 0 at the surface at X equals 0, right? So what that means is that minus K delta T delta X, applying Fourier's law, is equal to 0. So here we can divide the K and the negative out. So in this scenario for adiabatic surface, we'd have at X equals 0, comma, delta T delta X will equal 0. Okay? And then a fourth condition you might have would be convection. At the surface. Okay? So here, this is our surface. So here what we would know is H and T infinity. You might have some air going over the top of it or something. But here, our boundary condition would be this right here. Okay, because whatever goes into the wall by convection, that is also equal to the conduction on the other side of the wall. So here again, the conduction here at x equals 0 is just equal to whatever comes in by convection. So we can solve for temperature and say, well, let's just leave it at that, and I'll work a homework problem to demonstrate how to use this. But these are 4 typical boundary conditions that you would need to solve the heat equation. And if you have a transient problem, you would need an initial condition, and typically that initial condition would be something like at t equals 0, little t as in time, comma, the temperature is equal to some initial temperature. So typically transient problems will start with at t equals 0, the temperature of this object is 100 degrees Fahrenheit, or whatever it is. Okay? So that will be it for the heat equation. So let me work some homework problems next. Let me turn you around here so you can see. Okay, so that'll be it for the heat equation. And what I'll do next time on the next video is work some examples, some homework problems. And there's also a heat equation in cylindrical coordinates and spherical coordinates. We will do the cylindrical coordinates. I don't know if we'll do the spherical coordinates or not. Okay, so I will see you guys next time.